So important. So refraction. So let's just define it first of all. And this concept of refraction, you've all, I'm sure, experienced it before. So this is the idea that light will bend when traveling from one medium to another. So whenever it crosses over a boundary of one medium to another, it's going to bend. And you've probably seen this before, like when you look at things underwater or through glass, you notice that things kind of shift their location. It looks like they bend, or maybe it looks like they're smaller, or things like that. So this is this idea of refraction, that light bends when it goes from one substance to another substance. Now the reason for this is because something changes. When you go from, say, air to water, something changes. What does change? The speed changes. Okay, so the speed of light changes. Or the velocity changes. So I'm going to do an example here, just kind of an analogy, so you can kind of understand what's going on, and then we'll kind of apply it to light. So my analogy is going to be using a car. So let's take a car, for example. I'm going to draw the top view of a car. Let's see, how does this car look on here? It might be too big. Anyone have a Matchbox car on them? Okay, well, we'll have to make do with this. Alright, so here's our car. Our car is going to go from, say, cement to mud. Cement to mud. And the reason why is, well, we're going to create this analogy of speed changes. So where is it going to be fast? Where is it going to be slow? Fast, slow. Right? Cement will be fast, mud will be slow. Okay, so just like the speed changes. Now with light, how does the index affect the speed? If we're in a fast region, are we going to have a high index or a low index? Low index. So n is low. Remember, there's this inverse relationship. So n equals c over v. Okay, actually I should have written it like this. V equals c over n. So as n increases, what happens to v? Decreases. So it's this inverse relationship. So n is low, here n is high. So let's just watch the motion of the car here. Is our car's traveling down the road. It's traveling on cement, so it's traveling fast. So it's going fast, fast, fast like this. When this end of the car hits the mud, what happens to its speed? Slows down. So the right side of the car is going to now travel slow, whereas the left side of the car is still maintaining its speed. Okay? So because of that, as our car comes down fast, 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 this part's going to just get slower. What happens to the direction of the car? It's going to turn. What direction is it going to turn? To the right. So the car is going to shift its direction a little bit and now move off this way. Okay? So its direction has changed. So if I were to say follow the path of the car with, let's just say, a single line, so we have our car coming this way. Now our car is going to change its direction so that it looks like this. So our car is going to take a path that looks like this. Okay, so this is kind of the analogy. This is why light bends, or kind of the analogy of light bends. Let's just look at the light situation. So in the light situation, we might have on one side might be fast-moving light, which would be, say, in air, which has an index of 1. On the right side might be slow-moving light, such as water. Remember, everything is relative, so it could be, it's still fast in water, but compared to air, it's a little bit slower. Anyone remember N for water? Okay, so the same thing happens here. We have our light coming through. It's moving like this. In air, it's going fast. In water, it's going slow. And so again, if you imagine, here's our light beam. It's coming in like this, fast, fast, fast. The bottom part of the beam slows down. It's going to shift it and move off in this direction. Okay, so this would be like my laser beam, and it would bend from air to water. All right, let's label a couple things on this. Remember, this is my surface here. This is my surface with my interface or my boundary or my surface between the air and the water. And we're always going to draw a normal with the surface. So the normal is, again, the perpendicular to the surface. So if my surface rotates, I will also rotate my normal. Okay, so we're going to have an incident angle, just like with mirrors, we're going to have an incident angle. So we have, I can see 3 choices over here, A, B, or C. Which one is my incident angle, A, B, or C? B. So this angle right here, we're going to label as theta I. That's our incident angle. Okay, then we're going to also have a refracted angle, so I guess I'll label these. So theta I equals angle of incidence, or incident angle if you prefer, incoming angle. Okay, refracted angle is the angle that it refracts at, bends at, in the water. So we have a few choices. We have A, B, C. Which angle am I looking for, A, B, or C? B. All angles are with the normal, always. Okay, whenever I talk about angle, it's with the normal. Theta R equals angle of refraction. Okay, so anyways, is pretty much everything in math, or everything in science. Some guy comes around and figures out a formula to relate all this together. All right, so that guy's name in this case was Snell. And Snell developed Snell's law. It's going to relate everything all together. So Snell's law says this: the angle of incidence times the the index of refraction of the incident angle times the sine of the angle of incidence should equal the index of the angle of refraction times the sine of the angle of refraction. So Ni sine theta I equals Nr sine theta R. The key thing is just to remember that you have the two sides, right? So it's N sine theta equals N sine theta. So N sine theta one side equals N sine theta the other side. If you just remember that, the equation is pretty straightforward. So let's go ahead and do that for this problem. Let's say this was air, this was water. Let me give you an incident angle. Let's say this was 45 degrees. Can you go ahead and calculate for me the angle of refraction? Yes. Snell's law. So this is, basically it's N sine theta equals N sine theta, where the n sine theta is of one side, so one location, one medium, and then the other side is the other medium. So this might be air. In the problem we're doing right now, this would be the air side, this would be the water side. So you always have two things, right? Air to water, you could go water to glass, you could go water to diamond, diamond to air, whatever they are, you always have two things. And so in this case, we go from one to the other. So I'll give you about another 30 seconds, see if you guys can calculate theta r. So we'll call incident the air side. So I'm going to have 1 sine 45 equals 1.33 sine theta r. Okay, divide by 1.33. And then how do I get rid of theta r? Arc sine or inverse sine of whatever this is. Now according to my picture, what should be happening to the angle? Should it be greater or less than 45? Less. So always do that check on yourself. Make sure your answer is consistent with your prediction. What's the answer? 32 point what? So, by the way, make sure you're in degrees mode. If you're in radians mode, check it. Okay? What happens if I did the opposite? In other words, what would happen if I went from water to air? How would things change? Water to air. We'll just do it conceptually. We won't do it mathematically here. So if we're in water, is light traveling fast or slow? Slow. And if we're in air, it's now going to speed up. So let's use the model of the car again to see what happens to the angle. So in water, we're moving slow this time. So our car is going slow, slow. The right side hits the boundary first, but this time what's going to happen to the right side speed? It's going to speed up. So this time, instead of turning to the right, the car is going to turn to the left and take a new path that looks like this. So in other words, the light is going to bend, this time away from the normal. So if this is my theta I, and this is my theta r, if we go from a slow to a fast region, the angle increases. Back in the previous problem, we went from a fast to a slow, and the angle decreased. So both of those are important concepts. One of the things I want you to be able to do is to figure out how it's going to bend without doing it mathematically. So if you just give you a picture, you'll be able to draw how it's supposed to look.